Hello everyone, greetings of the day. Myself Omkarjan Sharma and I teach physics for NEET IIT. So today our lecture will be based on apparent depth in case of near normal incidence. So there are some prerequisites that you should know before starting the topic, and what are these? This is your reflection. Along with that, this is Snell's law that you should know. And other than this, there is this one relation about the refractive index that we'll start uh, discussing after these two. So reflection, if we talk about reflection, what is it? It is basically bending of light when light goes from one medium to another medium. Okay, and there are two concepts over this. When light goes from rarer to denser medium, it bends towards normal, and when light goes from denser to rarer medium, it bends away from the normal. So these are the concepts that we are going to use, and also the apparent depth is only the application of reflection. Now Snell's law. Snell's law is, it says that the product of refractive index of the medium from where the light is going multiplied by the sine of angle it is making with the normal is constant. That means if we are going from some medium mu1 to mu2, and with normal light is making some angle I, and in another it is making R, then mu1 sine I is equal to mu2 sine R. This is your Snell's law. Other than this, there is this one relation that you should know, that ratio of refractive indexes of two mediums can be also written as 1 mu 2. That is, refractive index Ri is representing just a refractive index of medium second with respect to 1. Okay, so these were some prerequisites. Now, other than that, if we talk about the practical application or where it is actually happening in real life, then it is, we can say, somewhere inside the sunrise and sun during the sunrise and sunset. What happens that we see sun little earlier than actual sunrise, and same is happening during the sunset. We see sun a little up to later, though sun is already set. So these are the cases that happens due to apparent depth. And now we'll try to find out a mathematical derivation for the apparent depth and how actually it is represented. So let's just start with the topic. Consider a medium of refractive index mu2, that T is the, or H is the whole thickness of the medium, and here object is placed at this point. Since if you want to see the an object, light will be passed from the object. So here light will go transfer from the O. One light, if goes normally, it will go without any refraction with the as it is. But if a ray goes at some angle with the normal like this, and at the interface refraction is going to happen because light is transferring from one medium to another. So if we draw a normal, what will happen? Light is going from denser medium to rarer medium, and when light goes from denser medium to rarer medium, it bends away from the normal, so it will make some angle R, and here it is making an angle I with the normal. So where the image is formed. Now, it is the main important concept. Image always forms at the point where two refracted rays will meet. Now, this is your refracted ray. If we trace back, then these two refracted rays meeting at this point, making a image. So, in reality, object seems over here. Though its actual real depth is here, actual position is here, but it appears over here. Then this is known as apparent depth. And this is your real depth. Let the apparent depth is represented by, this point is represented by h dash. Then we are going to find out a mathematical formulation for the whole concept. If we say this point is A, this is B, and this is your O, and this is your point D, then how we are going to make it? Let me magnify the image. Here it is as A, B. The distance between the 2 points is x, and this is your height h, and over here is actual image is the apparent image is appearing, that is your h dash, and this is your over here. So if we see at construction, this is your angle I, right? Then also this angle will be I, alternate angles, and also this line is making an angle R with the normal, so same over here it will be R, right? So we have two triangles, one is this, one is this, ABD, and other is ABO. So what we can do in triangle ABD, tan R can be written as, we can remember through the trick Pandit Badri Prasad Har Har Bole, perpendicular over base. So over here tan R can be written as perpendicular over base, that is x over h dash. Similarly in triangle ABO, tan I is equal to what? X upon h. Okay. Now why we have to find out this, or what is how it is going to help us. So using Snell's law, if we try to write down the Snell's law over here, what we are going to write? mu2 sine I is equal to mu1 sine r, right? If we say this, for these rays near normal incidence, we are saying near normal incidence, that means angle is too small. So here if angle is small, sine I can be equivalent to tan I, and sine R equivalent to tan R. Therefore, it can be written as mu2 tan I equal to mu1 tan R, or mu2 tan I, we can put the value from over here, tan I into x upon h is equal to mu1 x upon h dash. So from here we can get that h dash is your apparent dash, that will be equal to h dash is equal to what? Your mu1 divided by mu2 into h. That can also be written as h is your real depth. That will be real depth divided by mu2 upon mu1. So here we can again from the prerequisite we know that mu2 upon mu1 is equal to 1 mu2, that is refractive index of medium 2 with respect to 1. So therefore apparent depth is equal to h dash is equal to real depth upon refractive index 1 mu 2, that is refractive index of medium 2 with respect to 1. So this is your relation for apparent depth or real depth. Now another concept also arrives over here, that is normal shift. And what is this normal shift? So let me tell you this. In reality, if image is appearing over here and object is actually over here, image is appearing over here, then there is this shift from in the object, actual object, and actual apparent image. This shift between the two is known as normal shift, since it is the object is shifted at 90 degree to some another place. This is known as a normal shift. So how you can write normal shift? Simply normal shift, if represented by x, is equal to from the total height to the object where it is going to shift, that is h minus h dash, or it can also be written as, if you put h dash value over here, h minus h upon mu 2, that will be equal to 1 minus 1 upon mu into h. So, here we'll start with some numerical session. We have three questions to solve, and the first question is: a metal rod of mass m and length l slides on a rail, frictionless rail, and the resistance of the rail is given as r, and magnetic field is given perpendicular to the plane. So we have to find out some question part over here, that the velocity of the rod as a function of time. We have to find out the velocity of this rod, and other than that, the total distance traveled by the rod before it stops. And other than that, the last part of the question is asking about the total energy dissipated through the resistance R. So how we are going to approach this question? We have to find out that what's the concept of the question, or from where it is going to the question is asked. Actually, it is a question of electromagnetic induction, and from here it is the case of motional EMF. So how we are going to solve motional EMF? For those, we know that formula of the motional EMF is given as E is equal to VL. That is the EMF generated across a conductor when it is placed inside a magnetic field and moving with some velocity v. So let's just start with the topic. If E is the EMF generated, then current produced inside the conductor can be given as I is equal to E upon R as per the Ohm's law, and that can be calculated as VLV upon R. Also, since the conductor is carrying current and it is placed inside magnetic field, so it will experience a force, that is the force on a current carrying conductor in magnetic field, given by Fv is equal to VIL sine theta. Since magnetic field is perpendicular to plane, so over here theta is equal to 90 degree, or Fv is equal to VIL. We have already calculated I, so we'll put the value B L I. The value of I is BLV upon R. We'll put over here R. So what we'll get? V square L square V upon R as our magnetic Lorentz force. And also this force, as per the Newton's second law, what is it? Is equal to F is equal to mass into acceleration. So we can also write it as ma is equal to v square L square V upon R. Since this force is actually acting in the reverse direction, or it is decelerating the whole motion, so there will be a negative symbol, or F is equal to minus V L square V square L square V upon R. From here we can calculate acceleration minus V square L square V upon mr. So question asked can be arise in your thoughts, that why we have done this whole process, why we ended up to acceleration. Actually, it is asking about the velocity of the rod as a function of time. For that, if we know about the acceleration part, then we can easily calculate the velocity using the function of kinematics, that is acceleration is equal to change in velocity upon time. That is, we can start from over here. dv upon dt is equal to minus v square L square V upon mr. From over here, if we try to find out the function of using variable separable method, then function of v can be taken as to one side, or that will be equal to dv upon v is equal to minus v square L square upon mr dt. Therefore, we can calculate the velocity at some time t as a function of time it is asked about. So initial velocity is v naught. So we can integrate both sides. dv upon v, and variation of velocities from v naught to some velocity v is equal to minus v square L square upon mr integration of dt from time 0 to t. That will be equal to, since we know that integration of dx by x is equal to natural log of x, so from here we can calculate dV upon V is equal to natural log of V from value V naught to V is equal to minus V square L square T upon mr. And now we know if we put the limits, upper limit minus lower limit, and that will be equal to natural log of V minus natural log of V naught is equal to minus V square L square T by m r, right? So from here log m minus log n is equal to log m by n, that can be written as log V by V naught is equal to minus V square L square T by m r. And from here, if we want to omit the log function, since we are going to find out about the velocity, we have to take exponential function because exponential omits the natural log. So from here we can calculate V upon V naught is equal to e raised to power minus V square L square T by m r. And from here we can calculate V is equal to V naught e raised to power minus V square L square T by m r. And that will be your velocity as a function of time t. So your problem is solved. So now the second part of the question is the total distance traveled by the rod. So we have already calculated the velocity function. Now using this acceleration, we can calculate the distance traveled by the body. Since it is moving from some initial velocity and then it is decelerating, so after a time t, it is going to stop, right? So basically it is a deceleration motion. We have to find out the negative acceleration that we have already found out. A is equal to minus v square L square v upon mr. Now we have to find if distance, then somehow we have to write this acceleration relation in the form of distance and time. So we know that a famous relation about the acceleration, that is v dx upon dt is equal to minus v square L square v upon mr. As acceleration is equal to, we know that acceleration is equal to v dv upon dx. So from here we can write it v dv upon dx is equal to minus v square L square v upon mr. From here we can be omitted, and using this relation we can find out again with the help of variable separable method. Dv is equal to minus v square L square upon mr dx. That will be again integrating dv from the velocity v naught to some velocity v if we do, or 0 as it is stopping. So v naught to 0, dv is equal to minus v square L square upon mr into integration of dx from distance 0 to x. So using this we can find out the integration of dv will be v, and that will be your upper limit minus lower limit, but the lower limit is v naught and upper limit is 0, is equal to minus v square L square upon mr into x, right? So using this we can calculate 0 minus v naught is equal to minus v square L square upon mr into x. Or if you have to find out the total distance traveled by the rod before it stops, then you have to find out x, that will be equal to your x is equal to mr v naught upon v square L square. That will be your distance traveled before the rod stops. And that's your second part of the problem. Now, if we have to find out the next part, that is your total energy dissipated through the resistance R, and we have to prove it that it is equal to half mv naught square. So first we can do a simple thing. We can use the variables that we can use in the function. The force on this current carrying conductor inside the magnetic field as given by ma is equal to v square L square v upon r. Or using this relation, we can somehow find out the value of m in terms of v, l, and t. How? A acceleration can be written as velocity upon time. that will be equal to V square L square upon R, or M is equal to we can omit it from each side, and M is equal to V square L square T upon R. So why we did this, we are going to find out at the last. See, now if we say we have to find out the total energy dissipated, so the current is flowing through resistance R and it will be dissipated in the form of heat, and heat dissipated across a resistance R is given by H equal to I square R T. So we have already calculated I, and the value of I is BLV upon R, that will be equal to V square L square V square upon R square into R into T. And if we see, we can see R can be omitted from here. We'll find out that V square L square upon R into T into V square is equal to H. Right? So if you are trying to find out the total energy dissipated through the resistance, that will be your average heat, and that can be written as I square R by 2. From over here we can see that V square L square T upon R into V square, since M is equal to V square L square T upon R, so using the average of concept of average, H is equal to half M V square. If V is the velocity, half M V square. So that is your heat dissipated to the resistance R, or equal to half mv square. In a very normal way, we can use even the same concept, since the total work done will be stored in the form of heat, and initial velocity is velocity is v naught square. So this total kinetic energy is at the last is stopping and converted into heat. It can be normally considered using work energy theorem that change in kinetic energy is equal to work, and that work will be here stored in the form of heat, that is final minus initial, or half mv naught square is equal to heat dissipated, and heat dissipated is given by I square RT, and that can be the simple concept. So another way, so our next problem is nuclei of radioactive element A are being produced at constant rate alpha. The element has a decay constant lambda at time t. Calculate the number n of nuclei of A at time t. So here, so over here in the problem, what is given? The rate of production of nuclei element is alpha. That means if, for example, element is given represented by n, then rate of production dn by dt, rate means divided by time, is rate of production of element A is given by what? Equal to alpha. At the same time, it is also decaying, so rate of decay is given by dn by dt is equal to lambda n, as per the decay law. This is your decay law, okay? Okay, see carefully. It is saying, question is saying that this is the rate of production. I mean, alpha is the rate of production, this amount of elements are producing, out of which this is the rate of decay. This amount of elements are decaying. So therefore, total rate of production, total rate of production, that is dn by dt is equal to alpha minus lambda n, right? This will be your rate of production, because if we say like this is the total producing, out of which this amount is going to, decay. So what is left? This is left. So out of total we will decrease this amount, right? So from here, this is the equation we got. Now we have to find the, in question, calculate the number n of nuclei of A at time t. At some particular time t, we have to calculate the number of nuclei. How we are going to find it? Simply by variable separable method. What we will do? dn by alpha minus lambda n is equal to dt. Now we will integrate it for some time t, but as it is given that time t equal to 0, number of nuclei is n naught. That means here integrating both sides dn upon alpha minus lambda n from where n naught to some element n is equal to integration dt from time 0 to t. Now, how we are going to integrate it? By using variable separable method. For that, if we consider alpha minus lambda n equal to x, then what will be happen? You get minus lambda dn is equal to dx. Or in simple manner, dn can be written as 1 upon lambda dx. So from here, we can the whole value as dx upon x equal to upon 1 upon minus lambda, because dn can be written as minus 1 upon lambda dx is equal to t, and integration of dt is t. So from here dx upon x, integration of dx upon x is natural log of x. So from here natural log of x limits n naught to n is equal to, if lambda is taken to here, then it will be minus lambda t. So from here put the value of actual x, and x is alpha minus lambda n. Alpha minus lambda n, and n naught to n is equal to minus lambda t. So from here if we put upper limit minus lower limit, we will get natural log alpha minus lambda n minus natural log alpha minus lambda n naught is equal to minus lambda. So from here, what we get? Log m minus log n can be written as natural log of alpha minus lambda n upon alpha minus lambda n naught is equal to minus lambda t. Since we want to find the nuclei at time t, so what we have to do? We have to omit this log, and for omitting log, we have to take exponential on both sides. So taking exponential, what we'll get? Alpha minus lambda n upon alpha minus lambda n naught is equal to e raised to power minus lambda t. And again, if we want to find out alpha minus lambda n is equal to alpha minus lambda n naught into e raised to power minus lambda t, right? Using this, if we want to find the lambda n, that will be equal to alpha minus lambda l naught into e raised to power minus lambda t is equal to lambda n. This implies n will be equal to 1 upon lambda into alpha minus lambda n naught e raised to power minus lambda t. So that will be your nuclei at time t, and this will be our first part of the problem. Okay, so we are going to write it over here because this is going to help in our second part. So we get what we get: n is equal to 1 upon lambda alpha minus, that is 1 upon lambda alpha minus lambda n naught e raised to power minus lambda t. That is our n, right? So this will be our first part of the problem, and in the second part we are asked with some given value that if alpha is equal to 2 m naught lambda, calculate the number of nuclei of A if after the half-life of A. I mean, there are two values are given. Over here, alpha is given as 2 n naught lambda, and other than this, t is equal to t half, right? So, how we are going to perform it? We have to put these values over here, and from using those values, we are going to find out the final answer. Okay, so let's just do it. You try to find out n is equal to 1 upon lambda. Alpha will be equal to 2 n naught lambda minus 2 n naught lambda minus lambda n naught into e raised to power minus lambda into t half. Okay, so listen. T half is equal to, another way it can be written as natural log upon 2 lambda. So we can put it over here 1 upon lambda. If we take lambda common from here, lambda can be omitted. That will be 2n naught minus 2n naught minus n naught e raised to power minus lambda into natural log of 2 divided by lambda. So from here we can calculate n is equal to 2n naught minus n naught e raised to power minus natural log of, and that will be what? You get it, n naught, if we take n naught common, n naught 2 minus e raised to power minus e raised to power minus natural log of 2, that can be equal to e raised to our natural log 1 upon 2. I have done this, whatever I have done, listen carefully. We can write log of minus x, or minus log x is equal to log of x raised to minus 1 or log of 1 upon x. So I have done the same. Minus natural log of 2 can also be written as natural log of 1 upon 2. So we have done is, now exponential and log will omit each other. So we get n is equal to n naught 2 minus 1 upon 2. If we solve it overall, we get 3 by 2 n naught. So after a half-life, number of nuclei left from the initial nuclei will be 3 by 2 of n naught. So that's our first case from the second problem. And in second case, the alpha is given as 2 n naught lambda, and at the same time is tends to infinity. So in this case time is tending to infinity, so we'll try to solve this whole problem. N is equal to 1 upon lambda. Alpha can be put as 2 n naught lambda minus alpha minus lambda n naught e raised to power minus lambda t tends to infinity, so if you put it, it will be e raised to minus infinity, and we know that e raised to minus infinity is equal to 0. So what we'll get, n is equal to 1 upon lambda 2 n naught lambda minus 0, and that leads to n equal to 2 times of n naught. So after infinite time, number of nuclei will be 2 times of the n naught. So that's our second last problem. Now we will go for the last problem that we have to solve. So our last problem is, a solid cylinder of mass m and radius r is set in rotation about its axis with an angular velocity omega naught, then lowered with its lateral surface onto a horizontal plane and released. Okay, the coefficient of friction between the cylinder is mu, so we have to find how long the cylinder will move with sliding. Now question is asking, if we see carefully, question is asking about up to the time when it is sliding, means after time t it is going to start the rolling motion. So same question can be quoted as find the time after which the cylinder will start rolling motion. So two types of problem can be asked from the this single whole case, that how long the cylinder will move with sliding, and other than this, find the time after which the cylinder will start rolling. And so second part will be total work performed by the friction. So let's just start with the top problem. Here is the case of cylinder. M is the mass given, therefore mg will act downwards, and this normal direction will act, and it is also rolling with some angular velocity, initial angular velocity omega naught, and it is placed in a surface where friction is acting. Since friction is acting, so F will act in forward direction, given by, as mu is given the coefficient of it, that will be mu1. Now The problem is saying how long the cylinder will move with sliding. So for the sliding case is when velocity is either less than r omega or velocity is greater than r omega. Both are the undetermined cases. So we have to end to the case where problem can be determined. So in another way you can solve this problem is that by finding the case when it will start the rolling motion. And for rolling motion, what is the condition? B is equal to r omega. So velocity of center of mass should be equal to r omega. Omega is the angular velocity. So we'll find out the angular velocity at time t and velocity at time t, and then we'll equate these two equations, and from here we can find out the time. So first we have to find out the velocity. So let's just start. If we see force is acting in forward direction and this is the only force acting, then as per Newton's second law, force is equal to mass into acceleration. So F is equal to mu n, or that will be equal to mu mg, and ma can be written as mu mg. From here acceleration can be end up as a is equal to mu times c. So from here we got the acceleration. Now let b is the velocity at time t where it starts rolling or up to which it is sliding. So we'll get v is equal to u plus at. Since initial velocity is 0, it was not actually doing the linear motion at the initial time. So it will be equal to at, or in other way you can write it mu z t. So we got the b part from here. Now we have to find out the omega part. And how we'll find out the omega? Let's just see. Omega will be equal to, again with the same case, since it is moving with the initial angular velocity, that will be omega naught, and this friction will try to decelerate the cylinder so that at the final it starts rolling, and it can be calculated as alpha t. So here we can see we have to find out the alpha. Now how we can find out the alpha? We know for rolling motion tau is equal to I alpha. Here torque is provided by frictional force. That is F into R is equal to half mr square. That is your moment of inertia for the cylinder into alpha. So R is omitted. From here we can calculate alpha is equal to, as F is equal to mu times mg, equal to half m r alpha, or in other way we can calculate alpha is equal to 2 mu g by r. So as soon as we have alpha, we can calculate omega. That will be equal to omega naught minus 2 mu g t by r. From here we find out the omega. Now we'll solve the condition of rotational motion. That is v is equal to r omega, or in other way mu gt is equal to r into omega is omega naught minus 2 mu gt upon r, and if we take the values variables inside, you get r omega naught minus 2 mu gt is equal to mu gt. From here 3 times mu gt is equal to r omega naught, or as we are going to find out the time, so t will be equal to r omega naught upon 3 mu g. So this is our first case, where after which the cylinder will start rolling motion, or this is the time up to which roller will slide on the surface. So that's the first part of the problem, and now we will start with the second part of the problem, where we have to find out work done by the friction. Now we know, as we all know, we can put alpha over here, that if we use further it in any part of the problem. So we know that work done is equal to force into displacement. Since here only force is acting frictional force, so work done by frictional force will be equal to F into displacement. Now listen carefully. This frictional force will perform a linear motion. As a result, will give a linear displacement. But at the same time, this omega naught is trying to make the cylinder to the backward direction, right? So as a result, total displacement will be your displacement due to linear motion minus displacement due to the angular motion. So over here, we have to first find out the displacement, or in simple manner, we can write it mu mg. Displacement part can be calculated as, we know that s is equal to ut plus half at square. From here, we can calculate it as half a t square. That will be your total distance traveled due to linear motion, right? So half at square, and we have already a calculated over here, minus r theta, and theta is your angular displacement. Now for calculating theta, we have to use omega naught t minus half alpha t square. We have to put it over here, and that will be mu mg half mu g t square minus r into omega naught t minus half alpha t square. If we put the value of, we know that we have already calculated the time. Time was mu g r omega naught upon 3 mu g. From here we can put the values in the function. That will be mu mg half mu g r square omega naught square upon 9 mu square g square minus omega naught r t r omega naught upon 3 mu g plus half. We have already calculated the alpha part. We'll put it over here. 2 mu g by r into t square. That will be r square omega naught square upon 9 mu g. From here, 2 can be omitted, mu g can be omitted, and r is already multiplied inside, so r will be omitted from here. And from here, we can again, if we try to solve it all along, mu mg half mu g can be omitted, r square omega naught square upon 9 mu g, right? Minus omega naught r omega naught, that will be equal to r square omega naught square upon 3 mu g plus r square omega naught square upon 9 mu g. So if we watch carefully or try to solve it, we can take some function outside, and that will be mu mg into r square omega naught square upon mu g. That will be 1 upon 18 minus 1 upon 3 plus 1 upon 9. And if we try to solve it, we can solve it by using 2 by 18 and 2 by 18, 1 by 18, that will be equal to 3 by 18. 3 by 18 minus 1 by 3, that is can be written as 1 by 6. 1 by 6 minus 1 by 3. Over here, mu g part is omitted. We will get m r square omega naught square, and if we further solve it, we will get minus m r square omega naught square upon 6. So if we see carefully, this work done came negative. And now what the negative work means, that means frictional was acting against, or it was trying to make the roller to perform rolling motion. So actually this work is against or negative. So that's all about the whole problem case. Thank you so much.